decomposition and renormalization, and some applications to semi-classical quantization. Well, there's a lot of conservative dynamics on it, but not much symplectic geometry. Okay, so this is joint work with Aragão de Carvalho, which is a physicist at UFR Federal do Rio de Janeiro, and Maurício Peixoto at IMPA, and Alberto Pinto at Universidade do Minho in Portugal. Okay, so let me first give you an outline. So I'll tell you what is focal decomposition and what do you want to study when you look at focal decomposition. Then I'll try to give some motivation for the connection between renormalization and focal decomposition. And then I'll explain you the settings. After that, I'll try to give you an overview of our main results, connecting focal decomposition and renormalization of mechanical systems. And finally, by Peixoto and Tom in 1988. So the idea is that you look at a second-order differential equation with boundary value extremes given to you. And then your goal is to look for the number of solutions to that boundary value problem and to understand how this number changes when you vary the extreme points of the boundary value problem. Okay, so we have two extreme points, let's say T1x1 and T2x2, and let R4 be the set of all pairs of points in this Tx plane. Okay, to each point in R4, you associate the number of solutions to the boundary value problem in the previous slide. Okay, so let now to each point give an index I, the number of solutions to the boundary value problem. Then we define sigma I to be the set in R4 to which we can associate I solutions to that boundary value problem. Then R4 is the disjoint union of these sets sigma I. So sigma I define a partition of R4. And this partition is called the focal decomposition of R4, associated with the boundary value problem I've shown you before. Now, we can fix one of the endpoints. Let's say fix T1x1 equals to 0, 0. Then this set sigma I, this partition, defines you, or induces, a focal decomposition to R2, just by considering only the solutions to the boundary value problem, which start at 0, 0 and end at the point Tx in R2. So to this focal decomposition, we call restricted focal decomposition with base point 0, 0. And from now on, when I refer to focal decomposition, I'll be thinking about the focal decomposition of R2. Okay, so there is a famous example of focal decomposition, which is given by Peixoto and Tom. And it is the focal decomposition for the pendulum equation with base point 0, 0. Basically, it has indexes of all finite orders. So this is the Tx plane. And to every point, every final point, you can see the number of solutions connecting 0, 0 to that point by the index on these sigma sets. Basically, you have the odd index sets, which are open sets in R2, and you have two connected components, 21, 20 odd index. And then you have the even index sets, which are composed by 4 connected components. Okay? So, furthermore, the line x equals to pi and x equals to minus pi is as index 1, and the part of the plane above and below these lines are also parts of sigma 1. So the interesting part is the one lying between x equals to pi and x equals to minus pi. That's where you have small oscillations for the pendulum. Outside you will have full rotations. So that's why you get one solution in those parts of the plane. So let me keep this image here, since it will be useful later. So this is t, this is x. We have sigma infinity at 0, 0. There is an infinity of solutions connecting 0, 0 to 0, 0. You have sigma 0 on the top of the x-axis, since you cannot go from 0, 0 to some position at time 0 in finite time. So you cannot go in 0 time. Then you start having the even index sets at multiples of pi. And all of these lines are asymptotic to x equals to minus pi and x equals to pi. Okay. Another focal decomposition is for, well, simple one is for the harmonic oscillator. You have an infinity of solutions here, you have 0 solutions here, and then you have infinity of solutions at these points. And the rest of plane only has one solution. Okay. Okay, so now let me give you some motivation for the renormalization. So basically, Galileo observed that the oscillations of a pendulum have constant period. Okay, so this is the same thing as saying that the pendulum's period map is constant up to order 1, or in some other words, that you can consider the harmonic oscillator as a linearization for the pendulum. But if you look further in the Taylor expansion for the period map, you notice that up to starting from second order, this is no longer constant. So I've plotted here two period maps for these potentials. So on the left, you have the potential, so you have the period map for a mechanical system with a potential equals to 1/2 x squared minus 1/4 x to the 4. So basically, this is it, like this. And the other one is just 1/2 of x squared plus 1/4 x to the 4, which is this. Okay. So for this one, the period map is always larger than 2 pi. For the other one, the period map is smaller than 2 pi. And the key thing here is that different period maps induce you or give you different Peixoto-Thom focal decompositions, because the period map controls the way that the trajectories behave on this TX plane, or the number of solutions behave. Okay, so the main idea behind renormalization is the introduction of an operator, which we call renormalization operator, which acts on the space of systems in such a way that it removes its small-scale behavior and rescales the remaining variables to preserve some sort of renormalization. Okay, so if this renormalization operator, so under iteration of this renormalization operator, we converged some limiting behavior, then we say that this behavior is universal. And since this renormalization operator connects different scales, this universal behavior will be self-similar. So the renormalization operator that we introduce here acts on a family of mechanical systems that include the pendulum. Okay? So the motivation for the renormalization operator we choose comes from this focal decomposition and the approximately self-similarity of this structure. So basically, all these two even index sets are approximately self-similar. So we would like to exploit this to define a renormalization on the space of mechanical systems that have this sort of focal decomposition. Okay, so what we do? So we consider, so this is heuristic, it's not really the definition, I'll give you the definition later, but it gives you an idea of what we want to do. So basically, we look at this focal decomposition and move forward in time and consider some large integer n, okay, and here, and pi, and look only starting from that instant of time to the even index set here. So this should be sigma to n. Then we shift time so that the origin is now in n pi. Okay? But then you still have quite a lot of trajectories arriving there, to n. Then you restrict to small velocities only in such a way that you only have one solution here and two solutions there, and then your focal composition arises from that. Then we rescale back. Since we are considering only small velocities, we would be on a small strip around the t-axis. So we rescale back to get these even index sets asymptotic to x equals to 1 and x equals to -1. So this is the sort of action that this renormalization operator has on this focal decomposition. You go forward in time, you consider small velocities, and then we rescale back to have a meaningful size. Okay, so under iteration of this renormalization operator, we obtain an asymptotic universal behavior for the trajectories and the Peixoto-Thom focal decompositions for a large class of mechanical systems that include the pendulum. Both these asymptotic trajectories and focal decomposition are universal and self-similar. And moreover, we prove that these asymptotic trajectories are Hamiltonian, compute the action for these trajectories, so we get an asymptotic action, and we point out a possible application for these asymptotic results. Okay, so our setting will be given by mechanical systems with a Lagrangian function, which is a natural Lagrangian, just kinetic minus potential. And this potential function has to be non-isochronous. What I mean by that is that not all trajectories of this mechanical system have the same period. So it cannot be anything like the harmonic oscillator. Okay? And in a paper by Bolotin and McKay, they've proved that the non-isochronous potentials are translations and shears of the harmonic oscillator. So it's something which is considerably different from the harmonic oscillator. And we translate that by these conditions on the potential. So you want to have one point, Q star, where you can expand your potential V as a Taylor series like that. So at Q star, you have a critical point. The second derivative is positive in order for you to have periodic orbits nearby this Q star point. We make the third derivative 0 in order to preserve some symmetry that enable us or help us to do some estimates. But this is not a crucial assumption. We will be dealing with this case later, not in this talk, it's still work in progress. And then the fourth derivative has to be non-zero. It's some kind of a non-degeneracy assumption, and it distinguishes these two cases. So the case where you have an heteroplanic orbit here, and the case where you have a lot of periodic orbits. But the essential thing is that you have a one-parameter family of periodic orbits near this point Q star. Okay, so we can write down Euler-Lagrange equations and the corresponding Hamilton equations. And from the conditions on that potential function V, we obtain that there is this small neighborhood where you have a one-parameter family of periodic orbits, and therefore there is an epsilon such that for all initial velocities which have absolute size less than epsilon, the solutions to the Euler-Lagrange equation with initial conditions q star and v are periodic. And therefore, we can define the trajectories with these initial velocities, small initial velocities, by the solution of that Euler-Lagrange equations. And these solutions are well defined for all time. So we can introduce now precisely our renormalized trajectories. So what is the idea? So basically, you consider the trajectories q of the Euler-Lagrange equation and look forward in time to the instant np minus lt over omega. Omega is, well, the inverse of omega is the natural time scale of the system, in the sense that the orbits have period 2 pi over omega. So you look further into the future to an instant n pi over omega minus some quantity lt. That lt tells you that the period, it is to make the period be right. Since for some potentials the period is always larger than 2 pi, for the others is smaller than 2 pi. So you go to np and then you go to one side or the other depending on the sign of L in order to fix your period. Then you multiply the initial velocities v by omega and mu to take out the dimensions, and by a small parameter gamma. We call gamma the scaling parameter. So we are looking for results when n is large, so gamma is very small. And then we rescale back. So we move the point q star to the origin and rescale back space, multiplying by the inverse of gamma. Okay, so we are pushing quite a lot on these trajectories, mainly by using the multiplication by gamma. Notice that gamma will depend on t. T is some sort of asymptotic time. So we are choosing some periodic trajectories from a conservative system, but then we are destroying this conservative property. Okay. So basically what I want to tell you also is that this omega and mu are natural time and length scales, and all the variables v and t are dimensionless, and n-normalizable trajectories are also dimensionless. So we removed all dimensions from the system. Now, definition, we say that the asymptotic trajectories xl are given by that formula, v times sinus of lt v squared minus 1. At first sight, this might look like an harmonic oscillator, but then you look at it and you see that the period is not constant. It is varying with the initial velocity. So you don't have an harmonic oscillator, and this is nothing like any sort of linearization. So the first main theorem is the following. As n goes to infinity, the n renormalized trajectories converge to the asymptotic trajectories. Okay, so you cannot see the picture here. So in the picture I was plotting the trajectories. Okay, so mainly I was giving you for fixed instants of time, so t equals to 3p over 2. So the picture on the left should be something like this. Okay, so I'm plotting for this t, x of vt. So the final position at instant t as functions of the initial velocity. If you move forward to t equals to 7p over 2, this is the central figure, you should have something like this. Something like this. So this picture should be this. Okay? So this is a rescaling of that. And in the next time, you should see this inside a larger box which contains this and something more. So you can always see the previous time pictures inside each one of these. So this is the self-similarity for the trajectories. Unfortunately, it doesn't show up there. Okay, so now these asymptotic trajectories induce an asymptotic universal focal decomposition on the cylinder. So since we are considering only trajectories which are periodic with small velocities, we are only dealing with this strip. So you get the cylinder. Time times the position between -1 and 1. And we can define sets sigma I by being the pairs Tx in the cylinder to which the equation XL of Vt equals to X has exactly I solutions. Okay, so now each distinct solutions of that equation corresponds to an asymptotic trajectory connecting 0, 0 to Tx. And then for each I, this set sigma I contains all points such that there exist I solutions connecting 0, 0 to Tx. So we can give a focal decomposition for this cylinder. This is an asymptotic focal decomposition because it is induced by the asymptotic trajectories. Then we get this result. Okay. So there exists an asymptotic universal focal decomposition induced by the asymptotic trajectories. So this is the asymptotic focal decomposition. It is the same for all mechanical systems that we are considering, and it is the result of this sort of renormalization. Okay, we can move forward and can look at this asymptotic focal decomposition and define the index. So to each Tx on a set sigma I, we define the index of this point as the index of the set sigma I. And we can note that to each n renormalized trajectory xn, we have each one of these trajectories induce another asymptotic focal, not asymptotic, but another focal decomposition on the cylinder. Okay? By the same way, you look at the number of solutions that get to a given point starting from 0, 0. And then you can define a new n-normalized focal decomposition given by the focal decomposition arising from each of the n-normalized trajectories. And you define in a similar way the n-renormalized index. So the next result is the following. The n-renormalized indexes converge to the index of the asymptotic focal decomposition. So mainly what we get is we induced from the n-renormalized trajectories, so from the operator acting on those trajectories, we induced one operator acting on the focal decompositions, and this one is converging to the asymptotic focal decomposition. Okay, so now we can also extend our renormalization operator in a natural way to act on the velocities of our mechanical system. And again, if you consider velocities which are small enough, the velocities for the trajectories are well defined for all time. And then we can do the same thing. We pick up a velocity from the original mechanical system, q dot. We look further in time to the future. We rescale velocities so that we can consider only small velocities, and then we will we normalize backspace in order to get something with a unit size. Again, these are dimensionless. And in a similar way, we can define the asymptotic velocities and prove convergence of the n-renormalized velocities to the asymptotic velocities. The good thing is the following, is that there is a very strong connection between these two entities, the asymptotic trajectories and asymptotic velocities. And we might have lost this connection since we have chosen to pick up some sort of orbits in a conservative system, and we have destroyed the conservative properties during the renormalization. So it's a good thing that in the end, when going to the limit, we get back our conservative system. So basically, XL and YL, the pair, define a flow with the initial conditions given by 0V. Well, 0 should be the Q star. It's the point where you start. And this flow is Hamiltonian, and the Hamiltonian function has this form. So this is a sort of asymptotic Hamiltonian function for this class of systems. Okay, so now that you have the trajectories, you have the velocities, or momentum, as you like to think, and you have an asymptotic Hamiltonian. So we can define the action for this system. So basically, we define the action in the standard way. So let n be a smooth manifold, and m the cotangent bundle. And let delta be an interval in R, H a smooth Hamiltonian function. So a path omega in T1, T2 to M connecting P1 to P2 is a trajectory of the canonical Hamiltonian system MH if it is a critical point of that action functional. We can rewrite that as an integrand, function integrand depending on time, as in the bottom, and regard the integrand function as a Lagrangian. Okay, but since we are interested in looking at focal decompositions, the main concept is to look at the number of solutions connecting two boundary extremes, values. So instead of thinking of the action functional as depending on the trajectory omega, we rather think of it as depending on these extreme points. So instead of a functional, we'll have what we define as action correspondence of the trajectories connecting 2 points, T1, P1 to T2, P2, and giving as an image, so it's an application from a point to a set. So the image of 2 points, T1, P1 and T2, P2, is the set of R which contains the values of the action for all trajectories connecting those 2 points. Okay? So this is not really a properly defined function, but it can be dealt with, and it's useful to have it defined this way. Okay, so now we define the asymptotic action correspondence as the action correspondence associated with the asymptotic trajectories and velocities. And the key thing is that we get a nice formula for this action. So for a large class of Hamiltonian mechanical systems, we can renormalize and get nice expressions in the asymptotic limit. And inclusive can get an expression for the action. Well, this set V star, Vt, where the velocities are, is given by the focal decomposition, is the velocities that take you from some point 0, 0 to the extreme point Tx. So the cardinal of this set is the index of the focal decomposition for Tx. Okay, and now this is the asymptotic action correspondence for time f pi over 2, and it's the function of the, seen as a function of the final position x. Again, I don't know if you can see, but this is again a figure which inherits the self-similarity properties of the asymptotic trajectories and the focal decomposition. As time goes on, you get more and more of those figures, well, four-sided figures, and you get a self-similar figure. And as in here, you can look at the future picture and select some smaller box inside and see a previous time picture. Okay, now one application to semi-classical physics. So, in fact, focal decomposition can be seen as a first step towards semi-classical quantization. Okay, to illustrate this, let us consider the quantum mechanics one-dimensional propagator between an initial point x1 at time t1 and a final point x2 at time t2. And this can be expressed in terms of Feynman path integrals. So this propagator is the time evolution operator given by that exponential, computed between the position eigenstates x1 and x2. So you get that G and H is the Hamiltonian associated with our mechanical system. Now, this can be written as a path integral, where S is the action of this mechanical system, and the integral over Z on the first expression stands for the sum over all trajectories which connect x1 at t1 with x2 at t2. Okay, so we are more interested in the leading semi-classical expression for this propagator. So it is known that the resulting expression is that one shown there. Okay, what is all that? J in the upper limit of the sum sign is the same as the index in the focal decomposition. Sn in the exponential is the action for the n trajectory connecting the 2 points, x1 and x2. Sn2 is the second functional derivative of the action with respect to z, computed at this classical trajectory. And the determinant, well, the inverse square root of the determinant is called the Van Vleck determinant, and it's the first correction for the semi-classical expansion. So basically, under our renormalization procedure, we have built all the ingredients to start computing asymptotic limits for these propagators, semi-classical propagators. Okay, so how do we prove that first main result? So the convergence of the n renormalized trajectories to the asymptotic trajectory. First thing is to do change of coordinates of space and time. Okay, so you change and choose for units the natural length scales and time scales of the system. Okay, so we end up with some normalized Lagrangians where the potential is something like this or this plus higher order terms. So we will be interested in these two sorts of potential functions. Okay, so we can write down the Euler-Lagrange equation for this system, and we have got rid of all constants. Okay, and then using that change of coordinates, we have a good relation between the solutions for the normalized Euler-Lagrange equation and the solutions of the original Euler-Lagrange equations. So basically, the only thing we need to do is to go to the normalized Euler-Lagrange equation, work with that, study the properties of that equation, or the solutions of that equation, and then go back to the original system. Okay, so now let's forget for some instance the perturbations to these potential functions. So we only consider quartic potentials, so the ones of this form. Okay, and we denote by XL the solutions to this Euler-Lagrange equation. So we have two, one for the case of positive fourth derivative and the other one for the case of negative fourth derivative. Okay, now since the potentials, those potentials are quartic, we can use Jacobi elliptic functions and explicitly compute the solution to those Euler-Lagrange equations. Then, since we have that explicit knowledge, we can compute the first four terms of the Taylor series with respect to V of those solutions. Then we can use such Taylor expansions to study trajectories associated with the more general class of potentials by using perturbation theory and extending using an implicit function argument. Okay, so this is what you get when you do that. You compute explicit solutions, extend in power series, and you get this sort of expressions. So the first expression in red is the one is up to fifth order, so you get a very good description for the XL. The last one here is just the standard linearization expression. Okay, so we will use the first one, but we don't need to use the second term. So we just need to use the first term, which is V sinus of something times t, and that something is 1 plus v squared, or similar to 1 plus v squared. Okay, now we can look at the perturbed quartic potentials. So it's just the quartic potentials plus some higher order term. And we will denote by x of vt without the L, the solutions to the Euler-Lagrange equations defined by these perturbed quartic potentials. Okay, so these are perturbations of these two potentials only on a neighborhood of the equilibrium point. Away from the equilibrium point, you might have very different things. But on a neighborhood of the equilibrium point, these are perturbations of the quartic potentials. So then we use an implicit function argument, which is inspired in an argument developed by Bishnani and McKay in 2003. And we extend the estimates I've just shown you for the quartic potentials. We extend it to these perturbed quartic potentials. Okay, so let C2 0 be the set of all maps, all C2 maps, and I give you an interval with value 0 at 0. And let U be the linear operator that from C2 with domain C2 and range C0. So the operator just computes the second derivative of psi and some psi and fix the initial value of the derivative. So basically that is something related with the harmonic oscillator. Okay. Well, one of the first steps is to prove that this linear operator is invertible and its inverse is still a linear operator with bounded norm. Then you can prove a more interesting lemma. So we prove that for every time t positive, there exists constant, positive constants, delta 1, delta 2, delta 3k, such that for every velocity, initial velocity, which is small enough, and every epsilon, which is a C2 function which is 0 at 0, and it's small enough, then the ordinary differential equation, which is the perturbed Euler-Lagrange differential equation, has a unique solution x epsilon, which is C2, and it has initial values 0 and v. Okay? Furthermore, we obtain these estimates for the variation of the solution x epsilon with epsilon. So it is smaller than the size of your perturbation. So if you have a perturbation which is small enough, then you won't be perturbing too much of your solutions for your quartic potentials. And nearby the elliptic point, the perturbations are small enough. So this is the key lemma to prove this. So this is an estimate for the solutions of the perturbed quartic potentials in terms of the quartic potentials. So the distance is bounded by v to the 4. So if v is small enough and you want small velocities, then you are sufficiently close to your perturbed, to your quartic solutions. Those for which we already had good estimates. So you can extend those estimates to these perturbed quartic potentials, and the price we pay is that instead of having a v to the 5 in that last order, we have a v to the 4. But that's okay, since the only thing I want is a v to the 3. So I obtained, using this implicit function argument, I've obtained good estimates for the solutions of the Euler-Lagrange equation. Okay, the next ingredient in the proof is the period map. Okay, so since we are dealing with small velocities, we always have periodic orbits, and in particular, so if you have some velocities here, then we can estimate the extreme points of our periodic orbit, xm, x small m, and x large m, capital M. Okay? And since the energy is conserved along the orbits, and we've started with energy 1/2 v square, then we have these implicit relations in red for these extreme points of the orbit. Okay, so these are useful to define, well, there are other ways to define. These are useful to define the period map for the system. It's just given by that integral. This is standard knowledge from classical mechanics and Lagrangian mechanics. And we have chosen the value of the period map as 0 equals to 2 pi to make the period maps continuous and smooth. Okay, so notice that this is for this class of potential functions. Okay. So the period has to be 2 pi at 0. Okay, so now we can use the explicit knowledge of those two quartic potentials, and notice that by symmetry with respect to this axis, xm, x small m and x capital M have to be symmetric. And again, we can also estimate and say that they are order of the initial velocity. Then we can use the same sort of argument and get similar estimates for the extreme points for the orbits of the perturbed quartic potentials. Okay, so now for the quartic potentials, since we have an explicit knowledge of the quartic potentials, we can compute Taylor series for its period map. And again, we can obtain an expression for, well, a Taylor series for the period map for the perturbed quartic potentials, just lowering a bit the estimate. Okay, and why do we need the period map for? Firstly, it is key to determining the focal composition, but it also gives us the scaling parameter. So we define the scaling parameter Q and T as the velocity, initial velocity, that take us back to 0 after time np minus lt. Okay, so we have left from 0 with this velocity q. We know that at time np minus lt will be at 0. So we have done an integer number of half periods when we get to np minus lt. Okay? And that is the key thing to prove this lemma. So basically, using the period map, we can get an estimate for this scaling parameter, which is qnt equals to square root of that number, 8t over 3 pi n. And if you recall the initial definition of gamma in the definition of n renormalized trajectories, the gamma is exactly that, square root of 8t over 3 pi n. Moreover, using this scaling parameter, we can write down the time np minus lt. So forget the omega. Omega is equal to 1 for these quartic potentials. We can write np minus lt, that's where we want to be, as an integer number of half periods plus some r, a remainder, which is of this form. But since np minus lt is an integer number of these periods, we know that after an integer number of half periods, we are back at 0. Then we can remove the n over 2t from np minus lt, and we are left with this r. And that r is the argument you see inside the sinus and the cosinus and the asymptotic trajectory and the asymptotic velocity. So this is the strategy to get to those formulas. It's not any sort of linearization. We have used linearization to get some estimates over short intervals of time. But then we consider a large interval of time, and we will remove half periods. And what remains is a small number. So then we can put that small number inside a linearization and get the asymptotic formulas. So we have extended the validity of this sort of estimates. Okay, so basically this is an estimate which is for small times. No, it's for large times, but this is the sort of proof you have to do, this stuff that I was describing. And okay, so now I've shown you the tools we need to prove. So what remains to be done is to define the n-normalized maps, n-normalized trajectories for this two perturbed quartic potentials or normalized potentials, and then use all these tools to prove that the convergence to the asymptotic trajectory and asymptotic velocities. Okay, so basically, the energy normalized trajectories for these sort of potentials is the same one as shown you before, but you don't have to rescale time and space, and the asymptotic trajectory is the same. So then you prove the results using this strategy of playing around with NP minus LT and these half periods plus some remainder, and you get the convergence. To go back to the original potentials and original systems, you use that change of coordinates of time and space, and that lemma which connects the trajectories of these systems with the trajectories of the original systems. Okay, so what are we doing at the moment? What have you done? So we have proved a C2 convergence results for the trajectories. So what I've shown you is a C2 convergence results. So you can get sharper estimates and change the topology to C2 to get a better control on the derivatives of these asymptotic trajectories. We are preparing an extension of this renormalization scheme to act on trajectories living from any point on the energy level sets of this system. So notice that I was living only from the elliptic equilibrium with some velocities. So we're preparing an extension to live from any point on the energy level sets of these systems. And we are studying some results concerning the convergence of induced renormalized operators acting on the Hamiltonian functions. So basically we are proving that you can induce a renormalization on the Hamiltonian functions, and this renormalization will converge to the asymptotic Hamiltonian I've just shown you on the actions functionals. So after doing the Hamiltonian, we can do the action functions and prove the convergence. And the last thing is to prove the convergence of some renormalized propagators to an asymptotic propagator. All this using the information I've just shown you. Okay, so this is being done, and the next steps are to extend all this theory to potentials V with non-zero third derivative. So the non-zero third derivative introduces some sort of some lack of symmetry in these potentials. So the estimates are harder to get. Well, the estimates are not as good. The level of difficulty to get these estimates is the same, but you won't get estimates as good, mainly because there's lack of symmetry in these extreme points of the periodic orbits. And also, we are looking at applications to semi-classical quantum statistical mechanics. And in this one, there's still a lot to be done, mainly because the focal decomposition gives you the number of solutions for a number of solutions for the Euler-Lagrange equation connecting 2 points. These solutions are the critical points of some action functional, and this is the sort of thing that you need to compute the propagator in semi-classical quantum mechanics. But in the case of quantum statistical mechanics, you need the minimum of this action functional, not just a critical point. So what you have to do is, what we are doing is to define a sort of minimal focal decomposition. So instead of counting all solutions that go from the origin to a given point, you have to count the minimum, the trajectories which are a minimum for the action functional. Then you go over and go again, following the same steps, and you get to the semi-classical propagator for the quantum statistical mechanics. Okay, so thank you all for listening.